All right, so we have mentioned that the MLP uses a large number of parameters, and when you do not have enough data points, having too many parameters can be a problem to generalization. So comparing an MLP with a convolutional network, the convolutional network has far fewer parameters. And here we have a very simple example. This is the simple MLP we saw earlier, all right? And because we have a four-dimensional input vector x, and we have the hidden units that are three-dimensional, and we have a connection between every input element and every hidden unit. So each edge here represents a parameter, and obviously there are 4 times 3 equal to 12 parameters in this very simple network. And when the amount of data is constant, the more parameters it is, the more difficult it becomes to estimate them accurately. And often this could lead to some type of overfitting. So we could reduce the number of parameters in the following manner, right? We're going to apply 2 principles known as local connection and weight sharing. So first, let's look at local connection, which means that I'm only going to connect the units, the input units, to the nearby hidden units. Okay, so I'm going to connect my x1 to h1 and not to h2 or h3. Okay, I'm going to connect x2 to h2 as well as h1 because those are the adjacent ones, right? I'm not going to connect x2 to h3. This link does not exist. Okay, so this is the principle of local connection. The second principle is known as weight sharing. Okay, so I'm going to enforce that the green edge, all the 3 green edges have the same weight. And also all the yellow edges have the same weight as well. Okay, so if we do that, and we end up with only having 2 weight parameters for the green and the yellow. So we have reduced the number of parameters in the first layer from 12 to 2. And this is a 6-fold decrease, which is quite something, right? But what I've just shown to you is a 1D case of convolution. Now, I'm showing what I'm showing to you now is a 2D convolution where we have a set of weights that are denoted by the green square, and we are moving these green squares around in the space of the input. So our input is this blue matrix. And at each location of the green matrix, we're going to perform component-wise multiplication. So we're going to multiply the numbers that are at the corresponding locations. Okay, and we will sum the result and form a single value, and we're going to fill that value to the output matrix. Okay, so when the green matrix is at the first position, I'm going to once again perform component-wise multiplication, multiplying the corresponding numbers at the same position. After that, I'm going to sum all the products and put the sum in here. And then I will move the green square to the next location, which is to the right of the first location. And I will put in that number here, the sum of the product to that location, and so on and so forth, right? If you think about it, this is exactly the same idea that we have applied with local connections and shared weights. It is local connections because this first position in the output is only connected to a small location in the input, right? It's only connected to these 9 values in the large input matrix. And the second output value is connected to another 9 values and so on, right? So this is the principle of local connections. And this is also reflecting the principle of shared weights, because the green square that represent the weights is the same no matter where the green square is, right? So at all of these locations, the weights are the same. So I'm going to go to the next slide. And this is, again, the same idea, but represented in a different diagram. All right. So we have the green square, which we talked about earlier. Here it's written in the middle, and we call this the convolution filter. Okay. And we have the input matrix, which is the large matrix. And we're going to move the convolution filter around, first to the right, then down. And at any location, we'll compute the individual products and the sum. And that gives us the final result. And once again, this reflects the principle of local connections and weight sharing. Okay. This is yet another visual representation of the convolution network that we have. Okay. The interesting thing, though, of convolution network is that if you don't do anything fancy, if you just do the simplest type of convolution, then the output tends to be of a smaller size than the input. Okay. For example, if you have a 3x3 convolution kernel, or sometimes referred to as the convolution filter, then you could move in this 5x5 blue matrix, we could move 3 times, already move 2 times to the right. So its first position is here. Then I can move once and then twice. So that gives us 3 outputs in the output matrix. And similarly, I'll have 3 rows as well as 3 columns. So I'll end up with an output of 3x3, right? But my input is 5x5. So the output becomes smaller than the input. And to deal with that, I will use, in order to make the input and output of the same size, I will use some zero paddings. And of course, there are other types of paddings, but zero paddings are the most common. So I'm going to use some zero paddings around the input so that the output, the size of the output matrix, also referred to as the output feature map, will be of the same size as the input. So all these squares with dashed lines, these are the zero paddings I add around the original blue matrix, which is my input. Okay, so after I do that, we can see that the output becomes 5x5, which is the same size as the input. Okay, this is yet another visualization. So I do have a lot of different visualizations. This is yet another visualization where we have not only 1 input matrix, but we have 3 input matrices. Okay, so this is referred to as different channels. And it's very common to have inputs with multiple channels. For example, if you see a color image, typically each pixel is corresponding to 3 values: the red, the green, and the blue, right? So we have the spatial coordinates, the height and the width of the image, but at each point in space, we have 3 values, which can be written as 3 matrices, right? So maybe this matrix is my R, my G, and my B, okay? So if that happens, what would I do to kind of do the convolution? So the first thing I will do is that I will create 3 filters. So I'm going to first create 3 filters. And here I also have a bias. Sometimes you have the bias, but sometimes you don't. This is an option that you can control. A PyTorch, for example, and major deep learning frameworks give you the option to control that. All right. But going back to the 3-channel input, for each input channel, I'm going to create a 3x3 weight matrix, which is a filter. So collectively, I often refer to the 3x3 matrices together as one filter. Okay, so it's 3 times 3 times 3 for a total of 27 weights. All right, and the first small matrix here, the first 3x3 matrix, is used only on the green channel. The second one is only for the green channel, and the last one is only for the blue channel. So I'll do the multiplication at the corresponding locations, and I'll sum them together with the bias, and that gives me a single output in the output of this layer. And so that will, if I only have one set of 3 filters, I will end up with a single output matrix. But sometimes I also want my output to contain multiple channels. Okay, so it's actually really common to do that. And the way to do that is I'm going to introduce another set of filters and bias. And once again, the 3 filters each corresponds to one input channel. And at that channel, they're going to, the movement of the 3 filters are synchronous, right? So they are always at the same spatial location, but they are dedicated to a particular input channel. And the output, the sum of the product for the second set of filters goes to a second output matrix, which I'll refer to as the second output channel. Okay, so this is basically how we deal with multiple channels. We can have an arbitrary number of input channels and an arbitrary number of output channels by just changing how many 3x3 or n by n little filter matrices that we have. Okay. Oops. So my input size to any layer of a convolution layer is typically B times H times W times C. So let me explain what these are. B is basically the batch size, right? So we could be processing multiple input at the same time. When we will talk about, batched gradient descent, when we talk about stochastic gradient descent. But it's basically the number of data points we aggregate in one forward operation in order to utilize the GPU hardware, which is massively parallel, which has many computing cores that can do these kind of matrix multiplications in a highly parallel manner. So we do want to use a relatively large batch so that we can make efficient use of the hardware. The next one is the height, H, and the width, W, of the input image or the input feature map. And the last dimension is typically the number of channels, right? So this is known as an order 4 tensor. And let's say my kernel size or the filter size is k by k. So this refers to the dimensions of that little matrix. For example, in the diagram here, I have 3 by 3 kernel matrices or kernel size, right? So k is usually an odd number so that we have like a central pixel, okay? So the number of input channels, I'm going to refer to that as Cin, and the number of output channels, I'm going to refer to that as Cout. Okay, and imagine if I don't have any bias, I think it's most common these days to not have the bias weight. And then I can count the number of parameters that's in this convolution layer. And that would be the k squared times the number of input channel and then times the number of output channels, right? So here I have 3 input channels and 2 output channels. And my k is 3, so I have 3 times 3 times 3 times 2, which gave us 54 number of parameters without the biases, assuming the biases don't exist. This is the number of parameters that we have. And we can contrast that with a multi-layer perceptron and how many parameters the MLP network will have used. Assuming a 3x3 kernel size, I think this is probably the most common kernel size these days. And assuming the input number of channels, number of input channels to be 3, and the number of output channels to be 64, which is, I think, a very common number. And we can apply this equation and plug in the values, and that will tell us the total number of parameters as 1,728. If we were going to use the MLP network, okay, for a 32 by 32 input image, I would have a 32 times 32 times 3. That is the length of my input vector. And the length of my output vector will be 32 times 32. Excuse me. It'll be 32 times 32 times 64. That's the size of my output vector. And if I do the multiplication, this will be more than 200 million parameters, which is absolutely huge, right? So we can see that the convolution operation really helps us reduce the number of parameters that we have to learn.